In this lecture, we are going to compute the volume of a three-dimensional object. Just like when we were computing the area of a region, we sort of chop it into tiny strips, and then we use the length of the line segment as the integrand to build up the region, the area of the region. It's similarly when we are dealing with a three-dimensional object and computing its volume, we still are going to chop it off, along one of those axes, and then when you chop it, the cutoff will be an area. Then that area will be our integrand. We put it in integral, we get the volume. That's the basic idea. Okay, so in general, S is a solid, and you are S is between A and B. Then you just cut it along x-axis. So as you can see in here, I showed you the sphere. You cut it along perpendicular to x-axis. You have a lot of thin slices. Each slice, you imagine it's so thin, and it's a cylinder. Then it just have one area represent the whole thin slide, and then thin slice, and then that area is the integrand based on where x is. So essentially, this is x, this is y, and this is z. So when you cut it off, you get one. You pick an x here, and you cut the circle. It takes some imagination, but actually you're going to get a disk that we drew here. So at x value, you have a circle, and the circle has area pi r squared. Then the area of this red region, which is a circle, is our integrand. We put it in the integral. Okay, so our x, well, let's see the example. So the volume of a sphere of the radius r is v equals 4/3 pi r third. So we are computing the volume of a sphere with radius r, which is the thing. Our x, the lowest x you would have is here, the highest x you would have is here. So our x goes from negative r to positive r. So r. Then at a particular x, a of x will be the area of the chop off area or region is the red circle, or red disk. It has the radius y. So a of r, which is the area of that chop off region, is pi y squared. But we know that this is x, this is y. Together, you make this Pythagorean theorem right triangle. So we know that x squared plus y squared equals r squared. So y squared will be r squared minus x squared. Then I can compute the v, because I have the a now. You have x goes from negative r to r, and a of x is pi r squared minus x squared, parentheses here, dx. So this will be negative r to r pi r squared minus pi x squared dx. Pi r squared has no x, constant. Pi r squared x minus pi is constant, coefficient, and then I have x second. Raise it by 1, flip it. Okay, so that is the antiderivative pi r squared x minus a third pi x third. Then I evaluated at r and negative r. Bringing r, I have pi r squared times r minus pi times a third r to the third power, minusing the negative r version, pi r squared, negative r minus pi 1/3, negative r to the third power. This is pi r third minus pi over 3 r third, minus this is negative pi r third, and then I'm having a negative and negative, plus pi over 3 r third. So I'm having pi minus pi over 3, 2 pi over 3 r third, minus negative pi plus pi over 3, negative 2 pi over 3 r third. And I change them to addition, 4 pi third r to the third power. So we proved the theorem or the statement that the volume of a sphere, the volume of a sphere with a radius r, the volume of a ball of radius r, that's what I should say. I don't like sphere. Sphere to me is the surface, not the inside. The volume of the ball of radius r is v equals 4/3 pi r third. But here, what matters is the idea. You still chop the object along one axis, okay, the one that works, and then whatever you get, in this case, whatever region you get, if you are able to compute the area of that particular drop-off point, that's where you are, that's your integrand, a of x. Next example, we are going to find the volume of the solid obtained by rotating the region bounded by y equals x squared and y equals 9 about the y-axis. So you still need to graph y equals x squared and y equals 9 and have a sense what the region look like. But on top of that, you need to imagine how you are going to rotate it, in this case, about the y-axis. Remember, in this lecture, we are computing the volume of a solid three-dimensional object. And we are going to draw it on a two-dimensional object, which is your paper or my iPad. So it will be hard. Okay, it will take some imagination. But anyway, let me show you. So y equals x squared is the parabola, and y equals 9 is where 9 is, then you chop it off. That's y, that's x. Okay, and the region bounded by y equals x squared and y equals 9 will be this. Now, if you are going to rotate, imagine this sort of a portion of parabola. If I'm going to rotate it around the y-axis, what happens is, first of all, it's symmetric to y-axis. So when you rotate it, actually you are just rotating half of it. Same effect, because when you flip it, when you rotate 180 degrees, it will go here. So it's the same thing. So you can just imagine you are rotating half of it, and then this thing become circular. And it will look like this. You still have your x and y. Now I'm using the other color. This is what you started with, and when you rotate it, it becomes a circle. Okay. And here is 9. This point is 9. Y, x. So since obviously if you slice this thing horizontally, like perpendicular to y-axis, each slice will be a circle. That will be my a of x. Or in general, the idea is you always choose the axis that you are rotating on to be the independent variable, because when you slice it perpendicular to the rotation axis, you'll get a bunch of circles. So I pick a random y, I chop it off this sort of, I don't know, I don't even know how to call this shape, but if you chop it off, you're going to get this side and this side. Or what you can do is you go back to the original graph, look at when you chop it along a certain y, what you get. You get a straight line, a line segment, and when you rotate a line segment that is perpendicular to y-axis, and when you rotate it, you get a circle. Okay, now the question will be, when this is y, what is the r? If you need the circle, you need the area of the circle, you need the, so I need the area of this thing. You need the area of the circle, you need the radius. So first of all, our y is from 0 to 9. And for a particular circle, the area at y is pi r squared. But r, this point, r is essentially x, right? R is x on the parabola. So r equals x, which is square root of y. So pi a y will be a of y, the area of at y value will be pi times r squared radical y squared. That is pi y. Then, okay, you have the integral bounds, and then you have the chop off area. Then you can just put them together. Volume is from 0 to 9 pi, well, maybe I should use the formula first, a of y dy, where a of y is actually pi y dy. So pi is a coefficient, y I increase the power by 1, flip it, evaluate from 0 to 9. So this equals pi over 2 y squared from 9 and 0, pi over 2 times 9 squared minus pi over 2 times 0 squared. So this is 81 pi over 2 minus 0 times anything 0. So 81 pi over 2. That's the answer. Now you can try practice number 1. Example 3. Find the volume of the solid obtained by rotating the region bounded by y equals square root of 25 minus x squared, y equals 0, x equals 2, and x equals 4. Well, y equals 0, x equals 2, x equals 4, they're all horizontal and vertical lines. Those are easy. What is y equals square root of 25 minus x squared? Well, this actually is, if you square both hand sides, you have y squared equals 25 minus x squared, or x squared plus y squared equals 25. So pretty much, this is the circle with radius 5, but with the part that y is positive. Because when y is a square root, it has to be positive. Okay, so let me take this away. We have 5 and 5, negative 5 and positive 5. That's y equals square root of 25 minus x squared. Then we have 1, 2, 3, 4, 5. So it's between y equals 0, which is x-axis, and then we have x equals 2 and x equals 4. So that's 2, that's 4. This is our region. And we're going to rotate it about the x-axis. So again, before you imagining rotation, just look at how, if you are going to slide this area along x-axis, what do you have? You have these straight lines, line segments. So when you rotate these line segments, you get circles. And so this thing becomes, well, I only need this part, so it was 2, 2, 4, like this. So when you rotate it, first of all, it gets reflected to the bottom, and then the thing gets circular. That is the shape. But in particular, you pick one line. Here's x. Remember, what's the upper bound here? Square root of 25 minus x squared. And this line will go somewhere here. And when you rotate a line along, well, perpendicular, along a perpendicular axis, it becomes a circle. But with this radius. So when you have x here, a of x is a disk with r equals, you are having square root of 25 minus x squared. Well, if you want to minus 0, which is square root of 25 minus x squared, the length of this, which is the y of the circle. Then, of course, a of x will just be pi r squared. So we are having, first of all, x belongs to between 2 to 4. And our a of x is pi r squared, where r is square root of 25 minus x squared, then squared. So we have pi times 25 x squared. So 25 pi minus pi x squared. That's a. Then our v will be integral on 2 to 4 of our ax. 25 pi minus pi x squared dx. This will be 25 pi x minus pi times a third x to the third power 2, 4. Plug in 4, I'm having 25 pi times 4 minus pi times a third, 4 to the third power. Plug in 2, I'm having 25 pi times 2 minus pi times a third times 2 to the third power. So this is 100 pi, 4 times 25 give me 100, minus 4 to the third power is 64. So 64 over 3 pi. Minus 50 pi minus, this is 8, so 8/3 pi. 100 pi minus 64 over third pi. Now I'm removing all these parentheses, plus 8/3 pi. So combining these two terms, I'm having 50 pi. And combining these two terms, I'm having negative 64 plus 8. So it's still negative 64 minus 8 gives me 56 over 3 pi. So this will be 3 on the bottom, 150 pi minus 56 pi. And that will give me 94 pi over 3. And that's the answer. Again, let me say it one more time. It's hard to just imagine the rotation, but when you chop the base area perpendicular to the axis, you will have a line line segment that's easier to track, and just rotate that particular line segment and see if it gives you a circle, a disk, which means it's circle within also what's inside the circle, or you get a ring. So either way, you will be able to figure out the area. Now you can try practice number 2 and number 3. Example 4, we want to find the volume of the solid obtained by rotating the region bounded by y equals x and y equals x squared, but about x-axis. So y equals x squared is this way, and y equals x is this way. So first of all, you need to know where they meet each other. They meet each other at x equals x squared, or x squared minus x equals 0, x times x minus 1 equals 0, so x equals 0, x equals 1. This point will be 1, 1. So this is the region we are rotating about the x-axis, which is here. How does it work? Same thing, you can just imagine you chop it a little. So this line, when you rotate, it will not touch the x-axis. So what will happen is, first of all, it will be reflected to the other side. Let me use purple. To the other side, and this point particular will become a circle. This point particular will become another circle, and everything in between will be this. Everything in that plane between the two circles, and then also on the back. So you are getting a ring. Okay. And in this ring, what happens is, that's what you get from that purple. The inner radius is how far you have from the x-axis to the lower point here. So to the lower point here. And that is y equals x squared for particular x. So the inner will be x squared, and the outer is from, I'm running out of color, from here, that's inner circle and that's outer. So it need to reach the higher one, which is y equals x squared. Y equals x on top. This is y equals x. So x. And you are looking at the area of the ring. So the area of the ring is the area of the big circle minus the area of the little circle. So pi x squared minus pi x to the 4th power. That's a of x. And our x goes from 0 to 1. And our v will be from 0 to 1. Then the area, pi x squared minus pi x to the 4th dx. So pi x third, raise it by 1, flip, minus pi, raise it by 1 and flip, 0, 1. Pi over 3 x third minus pi over 5 x fifth, 0 to 1. Plug in 1. Pretty much you only have the coefficients. And plug in 0, you have nothing. The whole thing turns into 0. So the whole thing is gone. We are having pi over 3 minus pi over 5, and that is 15, 5 pi minus 3 pi, which is 2 pi over 15. And last, here I'm having this remark to show you before this example, example 1 through 3, our region that we're rotating lies on the axis. So you end up with circles. You end up with the cross section, the chop off area. The cross section are disks. But in this case, example 4, the region that you are rotating does not lie on the rotation axis. So the axis is here, but what you are trying to rotate is this one. So it doesn't lie on the x-axis. Like x-axis is not part of the region. Or in general, the rotation axis is not part of the region. So when you rotate it, you will have a ring, okay, with a hollow inside rather than the whole thing is filled. Yeah, and that is an observation I want you to see. And this thing is called a washer because it looks like a washer. Okay, that's it for this lecture.